Scientists just detected a major shift beneath California, and it's raising new concerns. Underneath a quiet county park south of San Francisco, in a stretch of oak-covered hills most people have never heard of, scientists have been measuring something that moves a few centimeters a year and yet may decide the fate of millions of people. The place is called Sanborn County Park in Saratoga, California. It sits almost directly on top of one of the most dangerous fault lines in North America. And in the last few days, new research out of that park has forced geologists to reconsider how fast the ground beneath California is actually moving. This is not a story about a single earthquake. It is a story about several independent lines of scientific evidence, developed by different research teams over different timescales that have all converged on California within the same narrow window of days. Some of that evidence goes back to the start of this year. Some of it is only days old. Taken together, it paints a picture of a state whose underground structure is more active, more complex, and in some places more dangerous than earlier models suggested. To understand why this matters, it helps to start with the basic geography. California sits on the boundary between two of the planet's tectonic plates, the Pacific Plate and the North American Plate. That boundary is not a single clean crack. It is a tangled network of faults, the largest and most famous of which is the San Andreas Fault, an 800-mile scar that runs almost the entire length of the state. The San Andreas produced the 1906 San Francisco earthquake, one of the most destructive events in American history, and it was also responsible for the 1989 Loma Prieta earthquake, which struck during a World Series game and killed 63 people. Californians have lived with this fault for as long as the state has existed. What has changed recently is not the fault itself. What has changed is how well scientists understand it. The oldest piece of this story begins in January of this year, when a team of researchers led by seismologist David Shelley, along with Amanda Thomas, Catherine Materna, and Robert Schummel, published a study in the journal Science. Their approach was unusual. Instead of studying large earthquakes, which are rare and destructive, they studied swarms of extremely small earthquakes, tremors so weak that no person could ever feel them on the surface. By tracking thousands of these faint signals over time, the team was able to map something that had never been clearly seen before, a hidden and unexpectedly complicated fault structure beneath Northern California, in the area where the San Andreas fault system meets the Cascadia subduction zone offshore. What they found surprised them. According to Materna, one of the study's authors, scientists had generally assumed that fault lines track the leading edge of a subducting slab of oceanic crust as it dives beneath the continent. This new mapping showed that assumption breaking down in this particular stretch of California. The data instead pointed to what researchers are now calling a captured slab fragment, a broken-off piece of oceanic plate that appears to still be shifting deep underground, dragging small earthquakes with it as it moves. In plain terms, the boundary between two of the planet's great tectonic plates is not sitting exactly where geologists believed it was. It is somewhere else, and it appears to still be in motion. The research was funded by the National Science Foundation and conducted through the University of California, Davis, and it gave scientists their clearest picture yet of a genuinely active, moving structure underneath California that most previous models had missed entirely. That was the background. That was the slow-moving, already confirmed piece of the puzzle. It set the stage for everything that has happened in the past few days because it told researchers that California's underground plumbing is more dynamic than textbooks assumed. And then, this month, 3 separate pieces of new information arrived within 72 hours of each other, all pointing back to the same fundamental question. How much stress is building beneath California, and how fast is it accumulating? The first piece came on August the 19th, when the San Francisco Chronicle reported on new geological research from Kim Bliznyuk, an associate professor of geology at San Jose State University. Bliznyuk is an earthquake geologist, and for years she's been studying a specific stretch of the northern San Andreas Fault that runs through the Santa Cruz Mountains, south of the San Francisco Bay Area. Her research site is Sanborn County Park in Saratoga, where the fault runs directly beneath the park's hiking trails and streambeds. Bliznyuk's method involves something called slip rate, which measures how quickly two sides of a fault move past each other every year. It sounds like a small technical detail, but slip rate is one of the most important numbers in earthquake science, because faults that move faster tend to produce earthquakes more often, and faults under more stress tend to produce larger ones when they finally rupture. For decades, researchers working on the northern San Andreas assumed that the fault's speed gradually slows down as it travels south from San Francisco, first through what geologists call the peninsula section, and then into the Santa Cruz Mountains section further south, with some of that motion theoretically being redistributed onto neighboring faults, such as the Calaveras. Bliznyuk's research has not yet been formally published or gone through peer review. The United States Geological Survey was asked to comment on the findings and declined to do so, specifically because the work has not yet completed that review process. That does not mean the research is wrong. It means, honestly, that it is still provisional, and responsible reporting on it needs to say so clearly rather than presenting it as settled fact. While that story was developing, a second and completely independent piece of research was moving through a different scientific pipeline entirely. On August the 20th, one day after the Chronicle's report on Blisniuk's fieldwork, a separate study appeared in the Bulletin of the Seismological Society of America. This paper was authored by Oliver Boyd, Robert Graves, and Evan Hirakawa, and it approached the problem of California earthquakes from an entirely different angle. Instead of measuring how fast a fault is creeping underground, this team simulated 5 real historical California earthquakes using multiple 3-dimensional models of the state's underground seismic velocity structure, essentially digital models of what different layers of rock and sediment do to a seismic wave as it travels upward from a fault rupture toward the surface. This is a critical companion piece to the slip rate story because it addresses a different half of the same problem. Blisniuk's fieldwork speaks to how much stress is building on a fault and how often that fault might rupture. The Boyd, Graves, and Hirakawa simulations speak to what happens after a rupture begins, tracing how the resulting seismic energy actually travels through California's complicated underground rock structure, and identifying where that energy might be amplified or dampened by the time it reaches homes, highways, and hospitals on the surface. Neither study by itself tells the whole story of California's earthquake risk. Together, they describe both how the pressure builds and where the shaking is likely to be worst once it is finally released. Then, on August the 21st, a third and much smaller event added an unplanned exclamation point to the same week. A magnitude 3.8 earthquake struck near Oakland in the East Bay. To be clear, and this is important, there is no scientific evidence connecting that small earthquake to either the Blisniuk slip rate findings or the Boyd, Graves, and Hirakawa simulation study. A magnitude 3.8 earthquake is a minor, fairly routine event for California, not a sign of an approaching major rupture, and nothing in the reporting around it suggests otherwise. What it did do, purely through timing, was remind residents of the San Francisco Bay Area that the fault network beneath their homes remains active in the present tense, not just in historical records or scientific papers. 3 stories, 3 days, 1 underlying subject: the ground beneath California and how much scientists still have to learn about it. It's worth stepping back here and asking how unusual this is. California produces new seismic research constantly. It is one of the most heavily instrumented and closely studied earthquake zones on Earth, home to the statewide California Earthquake Center, an extensive network of seismometers, GPS stations, and academic researchers at institutions from San Jose State to Caltech to the University of California campuses at Berkeley and Davis. New papers on California faults are published on a near-weekly basis. What made this particular stretch of days notable was not that new information appeared. It was that 2 separately conducted, methodologically unrelated studies, one built on ancient landforms and cosmogenic dating, the other built on computer simulations of wave propagation, arrived at roughly the same conclusion from 2 different directions within 24 hours of each other. California's fault system carries more energy and distributes that energy in more complicated ways than some existing models accounted for. To put the newest findings in a broader context, it helps to look at what the state's seismic hazard picture already looked like before this month's developments. According to a 2026 seismic hazard assessment, California holds roughly 16 million people and an estimated $3 trillion in building value located within what are classified as extreme seismic hazard zones. The United States Geological Survey has separately estimated that California faces a probability of 99.7% of experiencing 1 or more earthquakes of magnitude 6.7 or larger within the next 30 years. That is not a projection of a single catastrophic event. It reflects the ordinary, well-established seismic behavior of a state crossed by dozens of active fault systems. But when researchers model what a worst-case scenario, sometimes referred to informally as the big one, could look like along the San Andreas system, the estimated toll is severe. The USGS has estimated that such a scenario could produce roughly 1,800 deaths, around 50,000 injuries, and the displacement of approximately 500,000 residents, depending on where the rupture occurs and how it interacts with the state's dense urban development. Ahmed Ilbana, who directs the statewide California Earthquake Center, has described the financial exposure in similarly stark terms, suggesting that a total economic loss running into the trillions of dollars is a genuinely plausible outcome if a major rupture strikes in the wrong place at the wrong time. It is also worth naming plainly what remains uncertain here, because a story built on real science should be honest about the edges of that science. Kim Blisniuk's slip rate findings for the Santa Cruz Mountain section of the San Andreas Fault have not yet been formally published or peer-reviewed, and the United States Geological Survey has explicitly declined to weigh in until that review process is complete. That is a normal and healthy part of how science works, but it does mean the specific numbers involved should be treated as provisional rather than final. The connection between this slip rate research and the separate Boyd, Graves, and Hirakawa ground motion simulation study is one of shared relevance, not shared authorship or shared methodology, and the two teams were not working together. And the magnitude 3.8 earthquake near Oakland on August the 21st is, based on everything reported so far, an unrelated and unremarkable seismic event that happened to occur during the same news cycle, not a signal tied to either study. What can be said with confidence is this: the San Andreas Fault remains one of the most significant tectonic structures in North America, and the state of California continues to sit directly on top of it. Earlier this year, published, peer-reviewed research in the journal Science identified a previously unrecognized structure beneath Northern California, a captured slab fragment whose motion is being tracked through swarms of small, imperceptible earthquakes, revealing that the actual plate boundary lies in a different place than long-standing models assumed. In the past several days, new field research out of San Jose State University has suggested that a critical stretch of the northern San Andreas Fault near the San Francisco Bay Area may be accumulating stress at a more consistent and potentially higher rate than earlier estimates predicted, though that specific finding still awaits formal peer review. At nearly the same moment, a separately published, peer-reviewed simulation study offered new tools for understanding how a future earthquake's energy might travel through California's underground structure once a rupture begins. And to the south, around Los Angeles, other researchers have identified rising stress levels in a structural feature that could determine how far a future rupture might extend. Individually, each of these findings is a narrow technical contribution to a very old scientific question. Together, they represent something else, a moment where several independent research threads, developed over different timescales by different teams using different methods, converged on the same underlying message about California. The ground beneath the state is more complicated, more actively shifting, and in places more capable of concentrated destructive energy than some of the models built even a decade ago accounted for. That is not a reason for panic. Earthquakes are and have always been a defining feature of life in California, and the state has spent decades building codes, retrofitting infrastructure, and training emergency responders, specifically because of that reality. But it is a reason for attention, and it is a reason those closest to the research keep using words like plausible, consistent, and constant, rather than words like imminent or certain. To be fully transparent about where this information comes from, the reporting behind this story draws on a peer-reviewed study published in the journal Science by David Shelley, Amanda Thomas, Catherine Materna, and Robert Schummel, conducted through the University of California, Davis, and funded by the National Science Foundation. It also draws on reporting by the San Francisco Chronicle and ABC7 Bay Area on unpublished, not yet peer-reviewed research by San Jose State University geologist Kim Blisnuch, reporting that explicitly notes the United States Geological Survey declined to comment pending peer review. It draws on a peer-reviewed simulation study published in the Bulletin of the Seismological Society of America by Oliver Boyd, Robert Graves, and Evan Hirakawa. It draws on reporting by the Washington Post regarding stress accumulation on faults near Los Angeles, based on a study published in the journal Advancing Earth and Space Sciences. And it draws on publicly available hazard estimates from the United States Geological Survey and public comments from Ahmed Elbana, director of the statewide California Earthquake Center. Where a finding remains provisional, unpublished, or not yet peer-reviewed, that status has been stated directly rather than smoothed over, because a viewer trying to understand real risk deserves to know the difference between an established scientific result and a promising but still unverified one. There is one more thread to this story that deserves attention, because it connects California's fault system to a much larger, and in some ways, even more alarming structure sitting just off its northern coastline. Beyond California's own borders, off the coast of Oregon and Washington, lies the Cascadia subduction zone, where the Juan de Fuca plate is slowly diving beneath North America. Cascadia is capable of producing what seismologists classify as a megathrust earthquake, magnitude 9 or greater, among the most powerful category of earthquakes the planet can produce, along with a devastating tsunami. For years, Cascadia and the San Andreas Fault were generally treated by scientists as separate systems, connected only in the loose sense that they both sit along the Pacific coastline. New research published earlier this year has begun to challenge that separation. Scientists studying sediment cores pulled from the seafloor off Oregon found unusual layered deposits formed by underwater landslides that appear to record instances where a major Cascadia rupture and a major San Andreas rupture occurred close together in time, according to researchers who described the discovery as raising new concerns about a coast-wide earthquake sequence that could affect nearly the entire United States west coast within hours of an initial rupture. That single event remains the benchmark against which California's building codes, fire response systems, and emergency planning have been measured for more than a century. It is also part of why modern seismologists pay such close attention to any new data suggesting that stress along the same general fault system may be building in ways earlier models did not anticipate. The broader hazard picture around Los Angeles adds further weight to this pattern. The Washington Post's June reporting, based on the study published in the journal Advancing Earth and Space Sciences, described researchers modeling stress along faults close to the greater Los Angeles metropolitan area and finding that some sections had reached what the study's authors characterized as historic or peak stress levels, meaning the accumulated strain on those fault sections is now comparable to, or exceeding, levels seen before some of the largest earthquakes in the historical record for that region. The so-called earthquake gate identified just northeast of Los Angeles is significant because of a specific technical concern among seismologists, namely whether a rupture that begins on one fault segment can jump across a structural boundary onto a neighboring fault, effectively linking two separate faults into a single, much longer and more powerful rupture. A separate study, led by geophysicist Liliane Burkhardt of the University of Bern, working with colleagues affiliated with the Hawaii Institute of Geophysics and Planetology, used a computer model built from geological evidence, including tree ring records and sediment samples, to estimate how stress has built up over time along the San Andreas and San Jacinto fault systems closer to the Los Angeles basin. That modeling, extended up through the present day, found stress levels in some sections had reached historically elevated ranges, adding an independent line of evidence to the broader picture emerging from Northern California. California's history offers other reference points beyond Loma Prieta in 1906, and they help explain why researchers take fault stress data this seriously, even when a single new study remains unpublished. The 1994 Northridge earthquake, magnitude 6.7, struck the greater Los Angeles area on a fault that was not even mapped at the surface before it ruptured, killing dozens of people, injuring thousands, and causing damage estimated at more than $20 billion, making it one of the costliest natural disasters in United States history at the time. It remains a standard cautionary example among seismologists precisely because it demonstrated how a fault system can produce a major, damaging earthquake from a structure that existing maps and models had failed to fully account for, which is part of why new mapping efforts, like the low-frequency earthquake work published in Science earlier this year, are treated as more than academic curiosities. More recently, the 2019 Ridgecrest earthquake sequence, which included a magnitude 6.4 foreshock followed by a magnitude 7.1 main shock in the Mojave Desert region of Southern California, ruptured a complex network of previously unmapped smaller faults rather than a single well-known fault line, again underscoring how much of California's underground fault network remains incompletely understood even in an era of dense seismic monitoring. Ridgecrest caused relatively limited casualties given its size, largely because it struck a sparsely populated area. But seismologists have repeatedly noted that a comparable rupture pattern occurring beneath a dense urban corridor like the San Francisco Bay Area or the Los Angeles Basin would carry far greater consequences. That history matters directly to the newest findings because it illustrates the core justification researchers give for continuing to refine slip rate and stress models even along a fault as well studied as the San Andreas. The assumption that a famous, well-mapped fault is therefore a fully understood fault has been repeatedly undermined by California's own earthquake record. Northridge showed that damaging ruptures can occur on structures absent from existing maps. Ridgecrest showed that even a heavily instrumented region can host complex fault networks that seismologists had not fully characterized. And the Shelley, Thomas, Materna, and Scommel research published in Science this year showed that the plate boundary itself, arguably the single most fundamental piece of information in all of California seismology, may not sit exactly where long-standing models placed it beneath parts of Northern California. Viewed against that backdrop, Kim Blizniuk's still unpublished finding that slip rates in the Santa Cruz Mountain section of the San Andreas may not decline the way earlier models predicted fits into a broader, recurring pattern in California earthquake science, one where improved data collection keeps revealing that the state's fault systems are more intricate and, in places, more energetic than previous generations of researchers were able to detect with the tools available to them at the time. It is worth emphasizing again just how differently these various pieces of research were produced, because the diversity of method is part of what makes the overall pattern noteworthy rather than coincidental. Kim Blizniuk's work in the Santa Cruz Mountains relies on physically walking the landscape, identifying places where old stream channels, alluvial fans, and other natural landforms have been visibly offset by repeated earthquakes over thousands of years, and then dating those landforms using geochronology techniques capable of estimating ages tens of thousands of years old. The Boyd, Graves, and Hirakawa study relies on supercomputer simulations, essentially recreating past earthquakes inside a detailed three-dimensional digital model of California's underground rock layers to see how seismic energy would travel and where it would concentrate. The Shelley, Thomas, Materna, and Skumel study published in Science relies on a third method entirely, using dense networks of seismometers to detect and catalog swarms of extremely faint, low-frequency earthquakes, then using the statistical patterns in those swarms to infer the shape and motion of underground structures that cannot be directly observed. The Burckhardt-led study relies on yet another approach, translating physical evidence like tree rings and layered sediment into a mathematical model of accumulated fault stress over centuries. 4 different methods, 4 different research teams, all converging on some version of the same underlying message about the state of California's fault systems in 2026.